Got another 15 slides or so here for part 2 of NMR spectroscopy in chapter 14, talking a little bit more about where these signals appear when we're looking at an NMR spectrum. Now, what's important to know is that everything we're looking at when we're looking at a spectrum is relative to the reference compound. Okay? And the reference compound that we're going to see is TMS, tetramethylsilane. And notice how all of those protons on TMS are chemically indistinguishable from one another. They're chemically identical. So it's just going to give us one signal. Okay? And that signal appears at 0 ppm. And we'll talk about the ppm next. A couple of criteria for a reference compound, right? It has to be inert, can't react with anything that we would put in our tube. That wouldn't be good. It has to be easy to remove in case you have to recover your original compound, which chances are you want to do, especially if it's expensive. So TMS has a pretty low boiling point, 26, 27 degrees Celsius. So it can easily evaporate off of the solution. And so TMS meets that criteria. It's also nice because these methyl compounds, or sorry, these methyl protons that we have on the compound are in a nice electron-rich environment because silicon in the middle here is less electronegative than carbon. So by putting them in that electron-rich environment, that causes us to appear at a low frequency, okay, further to the right, upfield. So that's why we see TMS showing up all the way to the right at 0 ppm. So that's a key thing. You'll always see a spike at 0 unless it's been suppressed deliberately, and that corresponds to TMS, the reference compound. So what's that ppm business about? Okay. Well, that's the scale that's on the x-axis when we're looking at an NMR spectrum. Okay, we use the delta scale in NMR, and the position, as we just said, of TMS is defined as 0, and then all of our chemical shifts are a measure of how far the signal pops up relative to that reference TMS compound. So it's the difference downfield, the distance downfield from tetramethylsilane in hertz divided by the operating frequency of the spectrometer in megahertz, right? So hertz over megahertz means that our chemical shifts always end up being in part per million. Okay, so that's the unit that we see for NMR. And that's really a useful thing because it means that we get the same scale and the same type of spectra regardless of what frequency NMR we use, be it 300, 600, 1,000, right? Those machines get more expensive and they'll give us sharper spectra, but the scale does not change, right? An NMR spectrum is always going to look like this. You have your TMS reference compound at 0 up to a value of about 12 is the highest you would see. This one only goes up to 8. You would see it from up to about 12. And this is what a proton NMR spectrum looks like, right? For this compound in the yellow box, we've got 2 signals. Okay? We have the methylene protons, these 2 right here, giving us this peak. And then we have all of these methyl compound or these methyl protons giving us the peak here at around 1. Okay? There are only 2 unique protons in this compound. Thus, we see 2 signals in our NMR spectrum. Okay? Plus TMS, we're always going to see that. So just, always mentally know what that signal at 0 means, but it's not part of your compound, it's the reference. And we've talked about this, right? The greater the chemical shift, the higher the frequency. Okay? So our de-shielded electrons, or sorry, our de-shielded protons have a larger delta value. Bromine here, being right next to these methylene protons, pulls the electron density and causes the protons that are close to bromine to be further to the left, downfield, relative to the other ones that are further away. Okay. So between the first video and the second video, this is a nice little table here to help you remember those terms. Okay. It's comparing the left and the right. Things appearing to the left, as we alluded to in video 1, are things in electron poor environments. They're de-shielded. We call them, we say they appear downfield, which is at a high frequency and has a large delta value relative to the reference compound. And then all of those are the opposite for things that appear to the right. So let's look at another compound here with this nitropropane. What's going on here? Well, we have that NO2 group that's strongly electron withdrawing. Okay? So the closer we are to that NO2 and those electrons being pulled away from it, right, or pulled into it rather, the closer we are, the further downfield we appear at a higher frequency, a larger delta value. You see, the closer we get to that NO2, right, the further downfield these things are. Remembering downfield means further to the left. Okay, because that NO2 group is de-shielding the protons and pulling that electron density away. Okay, so the opposite of that, the stuff that's upfield on the right-hand side, right, lower values, means it's at low frequency because they're an electron-rich environment. They're more shielded. Okay, so that's a key idea here. The position relative to an electron withdrawing group, or as we'll see later, an electron donating group, is important. The identity of the group can affect those values as well. See here for the same compound, as I switch from fluorine to chlorine to bromine to iodine, the more electronegative something is, the more the de-shielding effect. Okay, so fluorine, you see, pulls it up to 4.5, whereas iodine down to 3.2. Okay, so the more electronegative, the more de-shielded something is, the further to the left. That's a really important idea. And that brings us to our first key table here in chapter 14. This is probably the #1 table to know. If you had to know only one, it would be table 14.1 here from the chapter. We'll have a couple tables throughout. Okay? But this tells you the approximate values of the chemical shifts for proton NMR, where they show up. And again, it's approximate because, as we'll see, there's some other factors that can change these. But you should start to get used to this and using this information. It's really good to know. If you can memorize it all, great. But that's kind of an uphill task. Okay? Try to commit the ones we see all the time, okay, like an aldehyde or a carboxylic acid, to memory. That would be more important for identifying a functional group than, say, some of the information in here. Okay, you'll use this table on your homework, for example, but I won't expect you to 100% know everything on this table. We can make it easier to quickly approximate these things by using something like this. Okay, this is more of a quick and dirty approach to telling what kind of protons are present. Okay, just dividing it up into ranges: 0 to 1.5, 1.5 to 2.5. 2.5 to 4.5, right? Then onward and upward. Okay. So just know that this is something I would expect you to know 100%. If I see a peak in one of these ranges, what does it correspond to? Okay. So we're going to talk about each one of these ranges, starting with the saturated range over here. Okay. And as we see here, we've got different types of protons. We've got methyl protons, right, with a CH3 versus methylene, CH2 versus methine, just CH, right? You've got a tertiary carbon there. So methine protons, as you can see, appear further downfield, right? They're at a higher frequency than your methylene and your methyl, okay? That's due to the fact that carbon is more electronegative than hydrogen, okay? So the extra carbons, the more carbons we get in the methine and the methylene, that causes the protons that are attached to be more de-shielded, just like a halogen would, but now to a little bit lesser of an extent. Okay, so in the saturated region, the further you go to the left, you go from methyl to methylene to methine. Okay, what else can affect our signal? Okay. Well, they can also play off each other. Okay, and notice the notation here, right? A, B, C. A, B, and C is not only identifying unique protons. Okay, so like, notice the two A's here. These are chemically indistinguishable. They're the same, these two methyl groups. Make sure you think about that in 3D to make sure that makes sense. Okay, so A, B, C, D, E, however many letters you have, label each of our unique protons, but they're also in order going down the alphabet, the higher frequency you get. So why does that happen, right? Going from A to B to C? Well, it's the proximity to an electron withdrawing group that's important. We just saw in the previous slide, right, jumping back, the number of other carbons you're bonded to is significant, yes, but so is the proximity to an electron withdrawing group. Okay? think about these methyl groups, for example, labeled A. Okay? They're further upfield than this methyl group, which is downfield, because it's closer to the oxygen, which is electron withdrawing, causing those methyl protons to be deshielded. Which really, this slide doesn't do a good job explaining. This kind of lists in text what we already said on the previous slide. What's notable here is the proximity to an electron withdrawing group. So here, these are both attached to the carbonyl, but C, the methylene protons here, are further downfield because it's a CH2 versus a methyl CH3. So two factors in your saturated region to look for. Number one, how many other carbons is it bonded to? The more carbons, the further downfield to the left. And number two, the proximity to an electron withdrawing group. What about for our sp2 carbons, okay, when we have protons attached to those? Well, first off, right off the bat, okay, you can see with these numbers here that if you have got a proton attached to an sp2 hybridized carbon, it's going to have a higher chemical shift and appear further to the left downfield due to two factors. Number one is the higher electronegativity of an sp2 carbon. Okay, we know by now that those are more electronegative, so it's going to cause them to be more deshielded. But this effect is more pronounced than if it was just electronegativity alone. The shifts are more notable. The effect that's really key here is called diamagnetic anisotropy. Okay, so I'm going to skip ahead here so you can see that diamagnetic anisotropy. That's what's causing these to have more notable shifts. Because really what's going on with each of these protons is that they're experiencing different magnetic fields. And anytime we have carbons that form pi bonds, we see this effect because those pi electrons are less tightly held and can kind of more freely move about. And they move in a circular pattern that approximates a magnetic field. And that effect, called diamagnetic anisotropy, causes protons attached to sp2 carbons to appear at higher frequencies than we would predict from the effect of electronegativity alone. Okay. So diamagnetic anisotropy, what's going on? Well, we have our external applied magnetic field, but those pi electrons, right, are also experiencing their own electromagnetic field caused by the molecule. And you can see the order that these are going in when it aligns with the applied magnetic field. They're going the same way. Okay? So the result is that, normally with shielding, it subtracts from the magnetic field. But here we see diamagnetic anisotropy for benzene protons. They end up sensing a larger magnetic field, than the applied magnetic field on their own, and thus they appear at higher frequencies. Okay? And we see the same thing here, same effect. We saw it with benzene before. Now we see it for alkenes and aldehydes. Same thing, those carbons that have pi bonds, diamagnetic anisotropy causes these things to appear at a further chemical shift because they, on their own, are experiencing a larger sensed effective magnetic field. So the one where we see it be the opposite then is for our sp carbons. And then these still have diamagnetic anisotropy, but it subtracts from the applied magnetic field. Okay? The induced magnetic field that's going on here is, notice the direction for the proton opposite that of the applied magnetic field. Okay? So if you have an sp hybridized carbon, right, it appears at a lower frequency, more upfield than what we would predict. Okay? So sp2 carbons further to the left than what we would expect. sp carbons further to the right. So that's some on the position, right? The frequency, the ppm values at which these peaks show up. And that explains some of what we saw in the table, 14.1, in the chart that followed it. Okay? One important piece of information that we'll continue to talk about. But another thing that we haven't mentioned so far is the size of the peak. Okay? And here, the size is notable. Okay? When we look at the peak heights and take the integration, take the integral of the value, right, the area under the signal, that's notable because it's proportional to the number of protons that are producing that signal. That's a really key idea. Make sure you're familiar with that, right? Write it down if you're taking notes. If we determine the area under a curve, right, by taking the integral, which the nice thing to that FTIR process, when the computer's doing all this, it does it automatically. Okay, so that's great. It'll do the integral for you. And the integral gives you the relative values of these things. Okay. So here we have a 1.6 to 7 ratio. Okay. Clearly, we don't have a molecule with 1.6 hydrogens and 7 hydrogens. Can't happen. It has to be a whole number. Right? So then we identify what the simplest ratio is that satisfies 1.6 to 7, okay, which is about 1 to 4.4, right? So that rounds up to 2 to 9. And sure enough, right, 2 protons and 9 protons. Okay, so those integral values will tell you the ratio of unique hydrogens that you have, which is a really useful piece of information. Okay, it's always an approximation. You're not going to get perfect whole numbers each time because you've got some experimental error in there. But you know, as long as you keep in mind that they're ratios, not absolute numbers, that's a really valuable tool. Okay, and so we'll finish with that thought, the integral ratio, which is a key thing. Okay, it is a ratio. These two compounds are going to show the same integral ratio, even though they're different. Okay? Both only produce 2 signals, and they're going to appear when we take the integral of the peaks as 1 to 3. And for 1,1-dichloroethane here on the left, it is 1 proton to 3 protons. Same integral values will show over here for 1,2-dichloro-2-methylpropane, but again, it's a ratio. So while it shows as 1 to 3, we have to take other information that's given to us, like the molar mass would be another useful thing, and figure out that it's in fact 2 to 6, because it's the simplest ratio, just like an empirical formula. But the integral value is a valuable piece of information. It gives us a lot to work with. And another thing we'll talk about in the next video, arguably the best part of NMR, is the shapes of the peaks and the splitting patterns. Yet another piece of the puzzle to start piecing these molecules together using this